The following is a test flight briefing for the Albatross aircraft before a test flight using simulated flight dynamics assessment. We start off with a weights and balance experiment with the Albatross propped up on 3 scales. As you can see in the top right corner, the location of the center of gravity on the z-axis, which is the longitudinal axis of the plane, is being moved. By moving the center of gravity back and forth, we can use the normal reaction on the scales to gauge whether the center of gravity is reached too far forward, as you will see, and the plane flips over entirely. However, once the center of gravity has been reached, which for this case is minus 0.01 meters, which in physical terms is 1 centimeters ahead of the origin, all 3 scales read 23 newtons, which confirms that the mass is being distributed equally across the 3 wheels, thus confirming that the center of gravity can be found using the normal reactions. Following this, we move on to the thrust test. This is done by setting up a scale at the nose of the Albatross. First, we go for a full-scale test, which is thrusting the Albatross at maximum speed into the scale, and we get maximum thrust at 30 newtons. However, we need to calibrate the RPM to the thrust, and as we can see, as we slowly increase the thrust, the numbers increase slowly. The negative sign is due to the orientation of the scale as we are moving into the scale. During the static test, it has come back that at 99 RPM, we exert 30 newtons of thrust. Therefore, a linear relationship can be made. The Albatross does begin to slip sideways, which can be said to impact the accuracy of the test. However, it still reaches a maximum of minus 29 newtons of thrust, which is 1 newton off the 30 newtons measured at the first thrust test, which does not make much of a change. And in the 30 newtons case, we can safely say that all the thrust went into the center of the scale. A second run-through has been done of the test just to get multiple readings, and for this one, you can see that the readings are more stable as the Albatross thrusts more evenly into the center of the scale. Following this, a static control test is done to make sure that the aircraft responds correctly to the inputted controls. We're using an Xbox 360 controllers to input here. The wind speed, direction, and elevation can all be changed, and as can be seen here, as any one of these factors is changed, the reaction on the wings changes. That is the amount of lift generated or the drag that is experienced by the aircraft. At the bottom right of the screen is the input mixing matrix, which will be used to determine how the controls behave. Here I am flicking the controls randomly to see how they respond to my inputs. You can see as I move the controllers, you can see the flaps or elevators move. As I change any one of the numbers on the input mixing matrix, it changes the behavior. As you can see, I've changed -1 to 1 here, and both inputs move in the same direction, whereas I change one sign to negative, they now move in opposite directions. The expected behaviors are that when rolling left, force on the left will be downwards while force on the right upwards, and vice versa. When pitching upwards, force on the tailplane will face downwards whilst force at the front will go upwards, and vice versa. Determining the correct configuration of the mixing matrix is important as it determines the control the pilot will have over the test flight. Here we have a first flight in which I am unable to even get the aircraft off the ground as the controls are not mapped correctly. After further tinkering with the mixing matrix in static control, I am able to find where the correct controls are and map the controller accordingly, which allows me to get takeoff. As you can see, I've inserted a video of the controller in the top right corner so that you'll be able to see the behavior of the aircraft as I take off. Here I thrust ahead at full speed. As you can see, it goes to 100 RPM and then prepare for takeoff. Takeoff is a bit delayed, but that's because I had thrusted my controls in the wrong direction. I am unable to get stability in the air as the controls are still not mapped correctly. As I try to turn one way, it turns the other way, making me lose control of the flight by overreacting and try to overcompensate by turning the other way, making the aircraft go into a barrel roll. However, I'm able to assert some form of control, but were unable to land in this case. To confirm that the controls were in the right place, I did a dynamic stability test with the same controller, which as you can see in the top right responds as I'd like it to. I do pitch, roll, and yaw tests to see how the controller reacts, and here you can see the rolling is correct and the yaw, which was done earlier, was correct. It should be noted that during the pitch, roll, and yaw tests, all of the movements are underdamped, which can be seen physically as they tend to oscillate the moment I let go of the controller. Following this, I do a wind tunnel test. These results can be imported into Microsoft Excel via the text file generated, which can be used to map graphs. First is the CL versus alpha curve. That as the angle of attack increases, the amount of lift generated increases. However, for all of them at around 15 degrees, the lift stalls, which means lift is no longer generated and the lift generated starts to reduce. Following this is the CL versus CD curve, also known as the drag polar. Here we can see that after 0.15, all the values seem to flatline. This is because the aircraft has stalled. Next is the coefficient of lift against the coefficient of moment, which is important for knowing how the airplane will respond as we change elevator deflection. Finally, CL against CM for different positions of the CG. This will show us how responsive the aircraft will be, i.e. how maneuverable to be at different CG positions. We can see here that Z equals minus 0.1, the aircraft will be resistant to pitching, i.e. it is more stable, where Z equals 0.1, which is further forward, the aircraft will be more responsive to pitching. In summary, my suggestions to the pilot would be to keep the Albatross's CG between 0.05 and minus 0.05 meters, with my personal suggestion being minus 0.01 meters. Secondly, during the takeoff phase, start the Albatross at 100% thrust. As seen with one of the earlier tests, starting it slow will only take it off the runway and onto the grass. The rest of the video needed to successfully pilot the Albatross will be in the video following this.